I want to pick back up in lesson 12.4, and I'm going to go back through and get all the examples I didn't get covered in class, and I'm also going to finish up with the binomial probability formula. So if you don't want all of this, pick and choose what you want, but everything will be here. So this example is the first example I skipped. You select 2 marbles at random from the bowl. For each situation, define the theoretical probability distribution for selecting a number of red marbles. So that's, last time we talked about it was the probability of getting a TO button. Now we're talking about red marbles on the sample space of 0, 1, or 2. So getting 0 red marbles, 1 red marble, or 2 red marble. And then we'll also follow up with being asked, is it a uniform probability distribution? So in A, the situation is you select 1 marble, put it back in the bowl, and then you select a second marble. And again, so putting it back is important. Keep in mind, we're talking about the probability. Red is the one that we're going to be looking at in the end. So looking at all the possibilities. If you look over in our bowl, we have green marbles, we have red marbles. So when you're drawing a marble, your choices are you're getting red or green. So I'm just going to take us through all the different probabilities. Keep in mind it's 2 draws, so if we start with getting 2 greens, I'm going to start there. So probability of getting green and green. Sorry, that G is kind of weird there. So, okay, this is a situation, folks. This was a little bit of a struggle of a quiz from what I've seen so far. Probability of, it's just 2 draws. So when there's 2 separate things, this is going to be a multiplication. So probability of the first green. As you look at green, what do we see here? We have 3 greens and 2 reds. So probability of getting the first green. It's going to be 3 chances out of 5 marbles. Now it's a second draw, so we're multiplying. Okay, it's 2 separate events. Notice I put that first marble back, so what's the probability of getting another green? And that is 3/5 again. 3/5 times 3/5, multiply straight across, and that is 9/25. I am going to work with decimals on these in the end, and so if you convert this to a decimal, 9 divided by 25 is 0.36. Okay, let's go through. What if we get green first and now red? So what's the probability of getting a green marble on the first draw? And that is 3 out of 5. I put back whatever I drew, and now what's the probability of getting a red marble? And you'll notice there are 2 red marbles, so 2 out of 5. 3 out of 5 times 2 out of 5, 2 out of 5 that is, 6 out of 25. If you divide that out, the decimal is 0.24. Okay, so those are the options if you get green on the first draw. Now let's look at red. What if I get red on the first draw and green on the second draw? So with that in mind, probability of getting red. Probability of getting a red, 2 out of 5. I put it back, probability of getting green. And that is 3 out of 5. Like the previous one, 2 out of 5 times 3 out of 5 is 6 out of 25, or 0.24. And then the last possibility you could have is probability of getting red the first draw and red the second draw. So probability of red on the first time, 2 out of 5. Put back whatever I draw. Probability of doing red again, 2 out of 5. Multiply across. 2 times 2 is 4. 5 times 5 is 25. And 4 out of 25, divide it. You have the decimal 0.16. Okay, so that's all the different probability options. We want the sample space for 0, 1, and 2. So probability of 0, 1, and 2. Keep in mind, we're talking red here, right? So when we say probability of 0, that's going to mean 0 reds. Which options involve 0 reds? And that's this one right here, the 0.36, because it was green and green. Okay, what are my options? And actually I will, there you go, there's your 0. What are my options for probability of 1 red? Well, 1 red You could have green and red or red and green. So that is the probability of 2400ths plus 2400ths, which is going to be 4800ths. And finally, probability of 2 red, and that's going to be right here. Probability of 2 red, 0.16. So right there is our probability distribution for the sample space of 0, 1, 2. And is it a uniform probability distribution? No, we ended up with 3 different probabilities. So it is not uniform. Okay, let's look at B. B just changes the situation slightly, and this time it is you select one marble and do not put it back. Then you select a second marble. So we're looking at all the same possibilities. Our probability is just going to change a little bit. So I'm going to start with probability. I'm going to go in the same order here. Probability of green and green. So first probability is not going to change. What's the probability of getting a green? That is 3 out of 5. Now, what's the key? I do not put it back. So that means instead of drawing out of 5 marbles, I'm drawing out of 4. Instead of having 3 green, I'm down to 2 green. So 3/5 times 2/4, or you can say 3/5 times 1/2. It is 6/20, or it reduces to 3/10. If I go decimals, 0.3. Okay, probability of green first, but this time red second. Of course, we restart. All 5 marbles are there, so probability of green is still 3/5. This time, probability of red. So we drew from 5. I'm keeping a green basically in my hand, so now I only have 4 choices. Probability of red. Well, I didn't touch the red the first time, so there's still 2. Oh, those numbers look familiar. 3/5 times 2/4. So multiplying across, it's 6/20. Reduces to be 3/10, which is the decimal. 3/10. Okay, so those were the options if green is drawn first. What about if red is drawn first? So red and then green. Probability of drawing red first, 2 out of 5 marbles. I draw a red and I do not put it back. Probability of drawing green. Well, I'm selecting only from 4 marbles, but I still have 3 green to choose from. So 2/5 times 3/4. Multiply across, 6/20, which reduces to be 3/10, which is also 3/10 as a decimal. And finally, the option of probability of red and red. Okay, probability of first red, 2 out of 5. I don't put that red back, so now I'm down to 4 marbles to pick from, and I only have 1 red marble to pick from. 2/5 times 1/4, 2/20, whoops, wrote the wrong thing there, 2/20, which reduces to 1/10, and that is a decimal 0.1. Okay, again, we are being asked about the distribution sample, so we're looking at the probability of 0, 1, and 2 for that sample space. Okay, again, remember we were talking about red. So probability of no reds, if you recall, that was green and green. So that is going to be a 0.3. Probability of 1 red. That happens on these middle 2. 1 red and 1 red. So that is 3/10 plus 3/10, which is 6/10. And finally, probability of 2 red. Well, that is down here on red and red, and that is 1/10. So right there is your probability distribution. And is it uniform? It is not. 0.3, 0.6, and 0.1. This is another example of not uniform. And if you notice, it's going to be more common that they are not uniform. Okay. The note down here at the end, hint, the sum of the probabilities of all outcomes is 1 in a probability distribution. I mentioned that in all the classes on Wednesday, so you've all heard it. But if you take these probabilities and add them up, probability of 0, 1, 2, all the options, it's going to add up to be 100% or 1 as fractions or decimals. So that is just a key fact to know right there. Okay? Okay. The next thing we're going to talk about, we looked at this probability distribution in class, looking at the experimental there. We're going to go over this one real quick. There's not quite as much to this one as there was the other one. But suppose that you select a student at random from the drama club and record the student's age. Define an experimental probability distribution on the sample space 14, 15, 16, 17, and 18. So in this case, we have age of students in drama club. There's 14 through 18, and then students. So last time this is what was labeled frequency. It just says students, but here is your frequency. In other words, how many students are that age? The 4, 7, 10, 7, and 9. Relative frequency is going through and figuring out what that is as a fraction that we can convert to a percent. So in this first case, 14-year-olds, we have 4 out of, they didn't tell us, did they? So we better get our total over here. 4 plus 7 plus 10 plus 7 plus 9. If I add those up, let's see, 4 and 7 is 11, plus 10 is 21, plus 7 is 28, plus another 9 is 37. So all of these are going to be out of 37. So for 14-year-olds, 4 out of 37. As a decimal, it's going to be 0.11. Might go on past that. I don't have that written down, but it becomes 11%. 15-year-olds. There's 7 of them out of 37. If you divide that, it becomes something along the lines of 0.18 or 0.18 something or 0.19. I have that it rounds to be 19%. 16-year-olds, there's 10 of them. 10 out of 37. Divide it, move that decimal 2 places right, and it's 27%. 17-year-olds, there's 7 out of 37 of them. Divide it, move that decimal 2 right, 19%. And 18-year-olds, you got 9 of them out of 37. 9 divided by 37, and then multiply by 100, move that decimal 2 right, and you've got 24% there. Okay, we weren't really asked any questions here other than figure out your probability distribution, which is what we just did, and then to graph it. So this one's already set up nicely for us. Age along the bottom, 14, 15, 16, 17, 18. Probability along the left. So we're just going to complete our bar graph. 14-year-olds were 11. So I'm going to make a bar approximately 11% high. 15-year-olds was 19%. So I'm going to make a bar approximately 19 high. Okay, 16-year-olds, 27%. So we're going to go up here a little bit past 25. And we've got a bar, 27% high. 17-year-olds are 19%. And 18-year-olds are 24%. Okay, so that is one more example of probability distribution using relative frequency and being able to graph it. Okay, on the next screen, we talked about binomial experiments. Okay, we talked about binomial experiments have to meet the 3 criteria. In example A here, it did meet the 3 criteria. In example B, it did not meet the 3 criteria. So we had an example where it was a binomial experiment and where it was not a binomial experiment. So we're going to go look at another set of examples here. Okay. Is the experiment a binomial experiment? If so, find the probability of success. And I think, you know what, I'm going to blow this up a little bit so I have a little bit more room to write. There we go. Okay, so is it a binomial experiment? So it has to meet those 3 criteria. You select a card at random from a set of 4 cards, or excuse me, from a set of 7 cards, 4 of which are labeled A and 3 are labeled B. Then you select another card at random from the cards that remain. For each selection, success is that card labeled A. Okay, so success is getting an A, basically. So, think about those 3 items. Are there 2 outcomes? Are the probabilities independent? Or are the results independent? And is the probability of success the same for every trial? Now, if you start thinking through those, there should be something that comes to mind here. Because what does it say here? Then you select another card at random from the cards that remain. What's that indicating? What I draw the first time, does that affect the probability of what I draw the second time? And it does, okay? So this one, I don't even really have to go any farther than that. I can see that they are not independent events. What card I draw the first time affects what cards are left and affects what cards I draw the second time. So this one is not a binomial experiment. Okay, it's not a binomial experiment because the events are not independent. Okay, the second card is dependent on what the first card was. Okay, the first card affects the probability of the second card is my explanation here. Okay, that is example A. Okay, example B. You roll a standard number cube 4 times. Assume that each time you roll the number cube, each number is equally likely to come up. So again, think like a fair die. For each roll, success is getting an even number. Okay, so are there 2 outcomes? Are the probabilities independent? And is their probability of success the same for each trial? Okay, well, I don't see any red flags, so I'm going to work my way through each one. Are there 2 outcomes? Well, success is getting an even, so there is getting an even number. Or what would be the other one? The other would be getting an even, or, and I'm going to put it as not even. You may have said odd. I understand that as well, but it's even or not even. Okay, even is the even or not, whatever is the general way to say it. So 2 outcomes. Independent. When you roll a standard number cube, does the first roll affect what I get on the second roll? No. And so I'm going to say that each roll is independent. So it meets the independent requirement. And then, again, as I mentioned, it usually goes along kind of with the independence, but is the probability of success the same each time? So probability of success in this case is the probability of getting an even? Is the probability of getting an even the same? Yeah, the probability of getting an even is always going to be 3/6 or 1/2. So this one is indeed a binomial experiment. That is a check mark there. Okay. Now, one last topic, and this is unfortunately the topic I did not get to in class. I may have to talk about more on Friday, we'll see. But the binomial probability formula, okay? For a binomial experiment consisting of n trials with the probability of success p for each trial, the probability of exactly r successes out of the n trials is given by this following formula. And I know I have this on the next page. But ways to get r successes in n trials, which is your combination, the probability of r successes, which is going to be p raised to the r, and then the probability of n minus r failures, 1 minus p to the n minus r. So let me advance my screen here. Okay, you see the formula up there. So let's look at this. A grocery store gives away scratch-off cards with a purchase of more than $100. Terrell has 5 scratch-off cards. What is the probability he has exactly 3 winning cards if each card has a 30% chance of being a winner? Okay, now, this is binomial probability formula. This has to be a binomial experiment before we can even proceed. So I'm going to check that real quick. And I'm not going to write it all out, but I need to know, is this a binomial experiment? Okay, are there 2 outcomes? Well, the probability that he has 3 winning cards. It can either be a winning card or a non-winning card. So I'm going to say that, yes, he has 2 outcomes. Is it independent? Does whether one card win affect whether the next card wins? One winning card has nothing to do with whether the next card is winning or not. So the events are independent. Is the probability of succeeding, probability in this case of winning, the same every time? And yes, because you either win, or actually it says each card has a 30% chance of being a winner. So you have that probability every time. Okay? And you either win or you don't win. So equal probabilities. So yes, this is a binomial experiment. So yes, I can proceed with my formula. Okay. Now, as we look at this, keep in mind when we did combinations and permutations, NCR, NPR, okay? N was how many you were picking from. 3 was how many you were picking. So if we try and figure out our NP, our N and our R here, how many are we picking from? Okay, Terrell has 5 scratch-off cards. So 5 is our N value because that's the total number he has. That's what we're picking from. How many is he picking? Well, he's trying to pick the 3 winning cards. And so 3 is my R value. Okay. And then probability is 30%. Now, as with most of the time when you use probability in a formula, you want a fraction or a decimal. I'm going to use 30% as a decimal, which is 0.30 or 0.3. Okay, guys, it's an intimidating looking formula, but it's plug and chug. Okay, so probability of R, the probability of 3 winning cards. So I put 3 in for R. NCR, so that's going to be 5 C3, the combination of 5 events picked 3 at a time, times P to the R. P is 0.3 raised to R, which is 3, times 1 minus P, so 1 minus 0.3 raised to the N minus R, so raised to the 5 minus 3. Okay, we filled in the formula, guys. Now, go through and do this in pieces. I would not recommend trying to put this all in your calculator unless you are just really skilled on the calculator. 5C3, that's a combination. Can you do that on the calculator? If not, ask me. Okay, I will gladly help you make sure you know how to do that, but you are supposed to know. That is a good thing to know. So 5C3 comes out to be 10 on the calculator. 0.3 to the third, I'm going to leave for the moment. And I'm going to go down here and clean up this next piece. 1 minus 0.3 is 0.7. 0.7 to the 5 minus 3, so 0.7 to the 2. If you can, I would just punch that all into the calculator at once. 10 times 0.3 to the third. Make sure you move out of the, into your exponent, times 0.7 to the 2. I have that is 0.1323 as a decimal. Since they used a percent in the problem, I'm going to go to a percent. And if we move our decimal 2 to the right or multiply by 100, we're going to be at 13%. So he has a 13% probability that he has exactly 3 winning cards. That is if each card has a 30% chance of being a winner. Okay. Now, B changes it up just slightly. Read the question, see what we need to tweak. Okay. Well, just slightly, but there's definitely some work to go with it. To the nearest tenth of a percent, what is the probability that Terrell has more than 3 winning cards? Now, so we're being asked for probability of more than 3. Okay. Probability of more than 3. What numbers are more than 3? And in this scenario, since we're picking from 5, that is 4 and 5. So what we're going to do here is we need to go use that formula to find 4 and 5. Okay? So I'm going to do that over here. Probability of 4. Okay, fill into your formula. Basically, instead of 3s, what are we going to put? We're going to put 4s, aren't we? Everything else stays the same. So it's going to, instead of 5C3, 5C4. 0.3 to the 4th. And 1 minus 0.3 to the 5 minus 4. Okay, I'm going to clean that up. 5C4 is 5 when you put it in the calculator. 0.3 to the 4th, I'll plug in a moment. And 1 minus 0.3 is going to be 0.7 to the 1st. I have a calculator answer of 0.02835. Practice on your calculator, okay? Now that's the probability of getting a 4. I'll change it to a percent in the end. I also need to repeat this with probability of getting 5 winning cards. So that was 4, now 5. So everything that was 3 earlier that we changed to 4s is now changing to 5s. So we have 5C5, 0.3 to the 5th, and 1 minus 0.3 to the 5 minus 5. Okay. 5C5, folks, anytime it's a combination, the numbers are the same. It's 1. 0.3 to the 5th. We'll get in a moment. 1 minus 0.3 is 0.7 raised to the 0. Well, if you want to make it this easy on yourself, anything raised to 0 is 1. This is a 1. All you have to do is 0.3 to the 5th. 0.3 to the 5th is 0.00243, according to my notes. Okay. So probability of more than 3 was probability of 4 plus 5. Probability of 4, 0.02835, plus probability of 5, 0.00243. Add those up, 0.03078, which is approximately, you move that decimal over 2, 3.078%. It did say nearest tenth, so that is 3.1%. Okay, so much easier when they ask for something exactly. Okay, we just wanted exactly 3 winning cards here, so it's probability of 3. On the second part, when they want more than 3, we have to look at the pieces. Okay, last one. Dana spins the spinner 6 times. Find the probability she gets a vowel exactly 3 times to the nearest percent. So, check yourself real quick. Whether you write anything down is up to you, but is a binomial experiment. Are there 2 outcomes? She could get a vowel or not a vowel. So 2 outcomes. Appears good. Are the events independent? Does each spin affect the other? Nope, spins are independent. So independent is good. And is the probability of succeeding the same each time? Yes, because each spin is good. So probability of success is equal each time. Okay, so binomial experiment. I've checked that. Okay, let's get our information. We're going to be doing the probability of how many times? Probability of 3. So that 3 is going to be my R. So right there, 3 is R. Okay. And then out of how many total times? And that is 6. So we've got 6 total times, and how many times are we trying to look at? We're looking at 3. And probability, we're going to have to figure that ourselves. They didn't give it. And it's probability she gets a vowel. So I want to say you tell me. Too bad you guys can't tell me through this video. Probability she gets a vowel. What do we have? A and E are my vowels. And so that is 2 out of 7. Okay, you could change that to a decimal, but it's not a nice decimal. So I'm going to leave it as a fraction for right now. Okay, probability that she gets a vowel 3 times. NCR. So that's going to be 6C3. P to the R. So the probability is 2/7 raised to the R, which is 3. Times 1 minus P. So 1 minus 2/7 raised to the N minus R. So raised to the 6 minus 3. I can clean this up a little bit. 6C3, combination of 6 things, picked 3 at a time, is 20. 2/7 to the third, I'm going to leave. 1 minus 2/7. Well, folks, 1, remember 1 as a fraction is 7/7. 7/7 minus 2/7 is 5/7. So 5/7 to the 6 minus 3 is third. Now, this is one that you can work to put in your calculator. It's doable if you know how to use your fractions. And it's something that I can help you in person with, not really over the video. So 0.169997195 is what I have written down. It says the nearest percent. So if we move that decimal over 2 and round to the nearest whole percent, it looks like we're talking about approximately 17%. Okay, guys, I know this was lengthy. Your next job is to work to get the Savas assignment done. Bring me questions, concerns, issues on Friday, or feel free to email me. And I will talk to you later, you guys later. Behave for the sub, please.